With 7.4, we look at exponential growth and decay. So today we're just focusing on population growth, and I just have one example problem. It does have multiple parts. Tomorrow we would, or not tomorrow, because I won't see you tomorrow, Wednesday, we will be looking at radioactive decay. So just different applications that can involve differential equations, separable differential equations. And they're actually all applications of the same type of differential equation, which is this general part that we're going to talk through first. So, and I know some of the words here got cut off by the hole punches. So we have if some general function y of t, this is the value of a quantity y at time t, and if the rate of change of y with respect to t is proportional to its size, y of t at any time, then we would get this differential equation. And this is actually, if you think back to 7.1 when we first started talking about differential equations, I had set up a population example and it was in this form. So this means the rate of change of y with respect to t, that's dy dt, or y prime of t. So the derivative is equal to some constant k times y, and again this y here is y of t, making then the derivative proportional to the function at time t, at any time t. So anytime you're given, all of the problems we're working through in 7.4 are differential equations or applications of this form where you're expecting the first derivative to be proportional to the function itself. But anytime you're given that information from the problem, rate of change being proportional to the function size at any time t, it's of this form. And then k is a constant. So this is a separable differential equation, and therefore it can be solved by the methods we learned in 7.3 and practiced the last couple of days, Thursday, Friday last week. So I'm just going to rewrite the differential equation we have here. And k, again, is just a constant. K isn't one of the variables. So first step, if you're solving a separable differential equation, what would we do first here? Yes, so you'd want to separate your variables. Again, this k really could be divided with the y, or you can leave the k where it is, but you want all the y's on one side, all the t's on the other. It's okay that we don't have anything with just t besides the dt. So I would personally leave the k where it is and divide each side by y multiplied by dt. So 1 over y dy equals k and then dt. So separate your variables. That can look different with different problems. After you separate the variables, what do you do? Take the integral of each side, integrate each side. So natural log of the absolute value of y, antiderivative of k with respect to t, kt. And then you need a plus c. And then you what? Yep, so then solve for y if you can. We can in this case. So to get rid of the natural log, raise each side as a power of e. And that right side, the entire thing is raised as that power, including that plus c. So here the e and natural log cancel out, so the absolute value of y equals, I'm actually going to rewrite this already. You could leave it like this. I'm going to rewrite it just so we can see why it works out to what we have down here. So remember, when you have a power where two different exponents are being added, I could split this as e to the kt times e to the c. And why I'm doing that is e to the c, if c is a constant, e to the c is also a constant. But then, how do we get rid of the absolute value? Yep, other side is just positive or negative. So it's kind of like getting rid of a square and square rooting type thing. Yes, so I'm going to leave it for now. I'm going to actually write the EC in front. So it'd be plus or minus e to the c times e to the kt. And then they will usually, or in the past, I know when I showed with a different example, we replaced this plus or minus e to the c, that's all a constant, and we replaced it with a, capital A. It doesn't really matter what variable you use, but I could write this as y equals a times e to the kt, where a would be plus or minus e to the c, or I really should state a could also be 0. So a could also be 0 in this case. E to the c would never be 0, so 0 would be a separate case aside from that. So this would be the solution, how we've written it before. But then, and I know it's given down here, but I want you to understand this, the question comes up, what is the significance of this coefficient a? So if you kind of compare the differential equation to the solution that we just found, notice that constant k is in the differential equation and in the solution. So k appears in both. We don't have an a anywhere though, so the significance of a is if this is your solution, and again, this is y of t, say you wanted to find y of 0, so at time 0, what does the function equal? So that would equal, if I substituted 0 in for t, I would have a times e to the k times 0, and that's just going to be a. K times 0 is 0, e to the 0 is 1, so this is just a. And y of 0, that would be at time 0, so that would be the initial quantity of y, whatever y is representing. If y is representing population, a would then be the initial population. Or if y is representing mass of some certain object, a would be the initial mass. So a is the initial value. And they will usually use, they don't use a when they're talking about, or rather in the notation they kind of change it for these specific applications. Rather than using a, they use y sub 0, or if you had p for population, you'd have p sub 0 just to show that initial value. So why this is important, anytime you have a differential equation that is in this form, where the first derivative is proportional to the function itself, you don't have to go through this process every single time. Your solution is always in this form, where it's y equals the initial value times e to the kt. So you would just need to know the initial value, you would need to know k, which if you were given the differential equation, you would know k from there. So it would always be in this form. So that's what's explained down here, that solution of the initial value problem, where this is your differential equation, this is your initial condition. The solution is always in this form. Okay, so we're going to be using this today to talk about population growth, and the differential equations we look at in this section are all in this form. So even if a problem, like I think the example we're going to go through, it doesn't necessarily state that we should be using this form, but in this section, in these practice problems, this is the form of the differential equation you're using, meaning this is the form of your solution to that equation. Otherwise, aside or outside of this section, you would be given some sort of information to know this is the form of your differential equation. So putting this into a specific population growth example, so if we let p be population, t be time, I'm just going to rewrite what we have here. So our differential equation instead would look like this, dp dt equals k times p. Okay, this is what we had actually set up when we started 7.1. And therefore, if we let the initial population p of 0 just be p sub 0, then this is going to be the solution of every differential equation of this form for population growth, our solution equation would be P of t equals P sub 0 initial population times e to the kt. So all solutions would be in that form. And then I also want to talk a little bit more about k. K is a constant, but in relation to this application, there's a specific name for what k is representing, and in case they ask you for it in a problem, I want you to know that they're really asking you to find k. So talking about the significance of k, for example, if I solved this differential equation, not the solution, but the actual differential equation, if I solved it for k, so I divided both sides by p, and I'm actually going to write it as 1 over p times dp dt. So that is what k is actually equal to. It's equal to the rate of change of population, that rate of growth, divided by the population size at that time t. So the rate of growth divided by the population size. And what that's called, in case a question asks you for it, the example we're going to go through does ask this. K then is the relative growth rate. So again, the relative growth rate is the instantaneous growth rate, so the derivative divided by the population size at that time. But if a question, like I said, we'll have this in the example too, if it asks for the relative growth rate, it's asking you to find k. And you can see that relative growth rate, again, I already pointed this out, k is in your solution equation as well. And then just a little bit of information before we get into our example. I'm just going to put kind of as an example here. Say we were given this differential equation. So dp dt equals 0.02 times p. Say you were just given that differential equation. First of all, this 0.02, that is your k value. And relative growth rate, what that means then, it's saying that the population is growing at a rate of 2% per year as long as t is measured in years, which t is often measured in years. Problems, though, should tell you what time is measured in. So if t was measured in years, this would be representing that the population grows at a rate of 2% per year. And again, the year, that it could be per hour, it could be per day, depending on what t is measured in, but it's often measured in years. So it is representing that percentage of the rate, or that relative growth rate. And then also from here, just to show you in the solution to this differential equation, we wouldn't be given just by what I wrote down the initial population size, but I could say the solution P of t would equal P sub 0, the initial population, times e to the 0.02 t. So I can substitute that k value directly into that solution. And then I would just have to know what the initial population is to be able to get my full solution. So there's really two things you need to know to write a solution equation in this section, or in this part of the chapter. You need to know the initial amount, and you need to know the value of k. As long as you know those or are able to find them, you can write your solutions. Okay, so this has been a lot of information, not going through a specific example, but are there any questions you have at this point? Otherwise, we'll actually put this into an example. Okay, and the example I have to go through in class, and this is between the two lessons we have, 7.4A, 7.4B. The examples I have to go through, and then the way the questions are also worded in the practice I have picked out could be different, so it's good to look at that practice and see. I'm not going through every type of version a question could be asked in, so just to make sure you would understand how to find certain things. So in this example, like I said, I just have one. It has multiple parts. And some of these parts are also just review of finding things from, you know, it could be review of something you might have done in pre-calc or something like that too. So in this example, we have a common inhabitant of the human intestines is the bacterium. I don't know how you say this, but E. coli. Sure, we'll go with that. Okay, so for E. coli, a cell of this bacterium in a nutrient-rough medium divides into 2 cells every 20 minutes. Probably important information. The initial population of a culture is 60 cells. Okay, so I'm actually going to have you look at all 5 parts they're asking us to find. So part A is asking us to find the relative growth rate. Remember, that is the K value in the differential equation, or that solution. We're trying to find K in that case. Part B, and I would recommend reading through all parts because, again, in part B, what I want to draw your attention to, it says, find an expression for the number of cells after T hours. So there it tells you what T is measured in. So we have something in the initial, or the way the problem is given, it talks about dividing into 2 cells every 20 minutes, but our T is measured in hours. So we have to keep that in mind as we're trying to find out our information. Then we'll find the number of cells after 8 hours, we'll find the rate of growth after 8 hours, and we'll find at what time the population would reach 20,000 cells. So if we go to part A, and again, like I said, it's assumed in this section you are dealing with that type of differential equation where the derivative is proportional to the population size. So in this example, I can say the differential equation would be of this form, dp dt, where the population is the E. coli cells. dp dt is equal to K times P. And that means the solution to this differential equation would be of this form. P of t would equal P sub 0 times e to the kt. And I'm just trying in part A to find K. Because really, in order to answer part B, finding an expression for the number of cells after T hours, that's really asking us for this equation, but we would need to know the initial population, which we're given, and we would need to know K, which is what we're finding in part A. So that's why it's asking us to find that first. So what I can do from here into this solution equation is I can substitute in the fact that I know the initial population is 60 cells. That's my P sub 0. So I then have P of t is equal to 60 times e to the kt. And then there needs to be some way that I can use this equation to find K. And I am given in the initial problem that 1 cell divides into 2 every 20 minutes. Ideas on how I could use that information, okay? So it would divide, so you're saying it would divide 3 times per hour. So really, I'm going to focus on this. So if we divide, into 2 cells every 20 minutes, I'm going to work through it this way. You are right, though, it would divide 3 times every hour. So 20 minutes, that t value would then be 1/3 of an hour. So rather than saying it would divide 3 times every hour, I can say it divides once every 1/3 of an hour. So I therefore know if I'm starting, so if I know P of 0 is 60, that was my initial population, how many cells will I have after 1/3 of an hour? 120, yes. Okay, so from there, how can I use that? Still, I'm trying to find K. Substitute that coordinate in. This gives me, this would go in place of P of T. This would go in place of T. So I can substitute in values here and here and solve that equation for K. So I would have, I'm actually going to flip this around and put the equals 120 at the end. So I have 60 e to the k times 1/3 should equal 120. And then I can solve that for k. So to solve for k, divide by 60. So e to the 1/3 k equals 2. Natural log each side. So then this e would be gone, so I would just have 1/3 k equals the natural log of 2 and multiply by 3. Now, don't change natural log of 2 into a decimal. Leave your values exact. So if I multiply by 3, I have k equals 3 natural log of 2. And I'm also going to be reviewing some things with logarithms with you. What's another way we could write 3 natural log of 2? Natural log of 8. So I'm giving you these hints if you're working through any practice or a question like this would appear on an AP test. It doesn't even have to do with this type of application, but if you get an answer like this on an AP test and there are no choices for 3 natural log of 2, but there is a natural log of 8 option, that is the answer. So you need to understand those are the same value. You can bring that 3 up as an exponent on the 2. So this is really the natural log of 2 cubed, meaning k is the natural log of 8. Okay, so that is the relative growth rate, natural log of 8. Okay, any questions on that? So in some way, whether you're given information or not, you need to be able to find the initial population and find that relative growth rate, the k value. So that for part B, an expression for the number of cells after t hours would now just be substituting this k value into our solution equation. And I'm going to show you different ways you could write this too. So you'd have P of t would equal 60 times e to the natural log of 8 times t. Okay, now this is a correct answer. You will not see an answer probably left like this though. So remember when you are multiplying exponents together, that means you have a power raised to another power. So just to show you why this is simplifying the way that it is, I could think of this as 60 times e to the natural log of 8 raised to the power of t. So that power raised to the power of t would get me those two exponents multiplied together. And the reason I'd want to do that is the e and natural log can cancel out, meaning I would get p of t is equal to 60 times 8 to the power of t. So you would raise the number 8 to whatever your t value is and then multiply that by 60, and that would give you your population at that time. Okay, so this would be the simplified way to write it, and no, you cannot multiply that 60 and 8 together. Okay, so I am fine if you were to leave something like this. This is correct. I'm just again saying multiple choice on the AP test. They don't leave answers non-simplified. So they would write the function this way. Yes, for short answer, this is a correct answer. Yes. And then C says find the number of cells after 8 hours. Just plug it in. So like I said, not all parts of this are necessarily new types of questions. So we would be finding P of 8. So 60 times 8 to the 8th power. And then here you just have to be careful with how you're calculating it. It will be a big number. So you should get yeah, 1,006,632,960 cells after 8 hours. Think about bacteria, that's kind of gross. E. coli? Like how fast it... Well, I would think if they're saying... It does say if it's in a nutrient broth medium, so in a certain condition, it's saying E. coli would divide this fast. Yes. I know nothing about E. coli other than there's some that's good for your body, but there's bad E. coli. Yes. How do you know this one's the good one? Okay. So maybe this is the good one, and then this not so bad. Okay. Part D. Find the rate of growth after 8 hours. So, yes, if it's asking for the rate of growth, what is that looking for? The derivative. Now, it's not as complicated as you might think, because up here, this is the derivative, dp dt equals k times p. So if we're finding it after 8 hours, we're saying dp dt is equal to k times your population after 8 hours, or at 8 hours. And you actually already found k in part A. You just found p of 8 in part C. So you're multiplying those two values together. So it's really the natural log of 8 multiplied by this 1,006,000,000. So this comes out to be 2,093,234,394. What would the units on that be? Cells per hour. Because T is just measured in hours. As you've seen in AP questions before, understanding units is important. Some questions just ask you for the units. Some free response questions, you get an entire point for having the correct units written down. Otherwise, if a question doesn't ask you for units in terms of free response, you don't, yeah. If you put units, they won't even look at them. I don't think so. If it doesn't ask for units, they don't pay attention to the units. Well, I wouldn't just write down random things on the AP test, but I'm almost positive they don't look at them if it's not part of the score. Okay, and then it says when will the population reach 20,000 cells? So this, if we go back to this function here, the population is 20,000. We're trying to find T. So this would be when 20,000 is equal to 60 times 8 to the power of T. So just quickly, and then we'll get to the homework quiz. How would you solve this for t? Divide by 60. Now I'm going to save all calculations until the very end, so I'm not going to write this simplified. So I have 20,000 divided by 60 equals 8 to the t. Yes, so you could, I didn't hear, Kai, what did you say? So you could do log base 8 of both sides, and I know a lot of you have a calculator where you can type in log base 8. You could also, you could take log of any base. So I really could here take natural log of each side. Yep, because then the t, as long as you take any log of each side, the 8 here won't cancel if I do natural log, but it still brings the t down. So I'd have natural log of 20,000 divided by 60 equals t times the natural log of 8. And then I just have to divide by the natural log of 8. So t is equal to, and I know this is messy looking here, but the natural log of 20,000 divided by 60 divided by natural log of 8. And yes, you would have to type those in. Those are two separate natural logs. So you can't combine them to just be natural log of 20,000 divided by 60 divided by 8. So I will put the answer down. You should make sure, though, that on your calculators you can get this. Actually, I should calculate it because I did not write down 3 decimal places for some reason. You could solve it that way, too. But then you might be spending more time trying to find the right window to see where they intersect and things like that if you're not. True. So it's about 2.794 hours.
This is the last homework my ever.